do think.
All right.
One of those things.
All right, here we go. We're going to go ahead and get started with our videoing thing, which does mean if you are in here not for videoing reasons.
Bye, Mr. Biggs.
All right, get some rest. If you're in here not for physics reasons, I'm going to ask you to keep it down so that you don't become immortalized on our recording. All right. I'm going to begin where my class left off, which was with FRQ number 3. I will at some point go back and re-record FRQs 1 and 2 in case you missed those. So we're going to do this a little out of order. We're going to go ahead and start with FRQ number 3, which I think was very highly talked about after the exam. We have this thing that exerts a restoring force, this little spring, with an unknown exponent, right? So we're told that the force is going to be b times x to some power of n. And the first thing we wanted to do is to indicate what things we should measure. I really hope people said to measure the force and the displacement. If you said to measure the force and the displacement, congratulations. You get a point. Yes.
What if we said measure the force and the displacement, and then also measure some other thing?
That you're probably fine. If you measure the force and the displacement, that should be okay.
Like the answer.
Oh, yep. You should be okay on that. If you mentioned like 7 extraneous things, they might be mad at you. But if you're, yeah. All right. The second thing to do is they want you to reduce experimental uncertainty. So what do? You measure it multiple times, right? You measure several different forces, several different displacements.
Yeah.
In order to, several different forces, several different displacements, in order to reduce experimental uncertainty. So if you said to do it multiple times, take multiple data points, excellent, congratulations, you will earn that point as well. So that's 2 points there. Now, the part that I think gave people a little bit of trouble is the part that fortunately was only worth 2 points. Well, 1 point for C and 1 point for D. All right, this is like a weird time to maybe put your chemistry hat on, which is we need to find that exponent. And so we're going to do a somewhat unusual thing, which is we're actually going to take the log. You can do a log base 10 or a natural log. It doesn't really matter the base. We'll just do ln. If you take the natural log of the force, you'll take the natural log of the other side as well. The funny thing about the other side is the way that natural logs work is this is the natural log of b plus n times the natural log of x. Why did I just write log? I meant to write ln. N times the natural log of x. So what you can actually do is if you put on the horizontal axis the natural log of your displacement on the vertical axis you put the natural log of your force, what you're going to find is you'll get a linear graph ln x and you'll get ln fd. And in this case, what will your slope be? Well, if this is your y and this is your x, what would your slope be? N. Your slope will be n. What's nice here is that if you do this log-log graph, the slope of that graph will be exactly n. And notice we've got this part, if you think y equals mx plus b, your y-intercept, your vertical intercept, will be the natural log of that b number that you're looking at. So you can actually get both numbers by making a log-log graph. Now, in the event that you did not get that correct, you probably didn't get either of the points there, but congratulations, that is 2 out of 10, I think. 2 out of 10 for the FRQ. So, so in this case, we did have to do a log-log graph, which I know is a thing you occasionally do in chemistry with certain reactions. And it's just a thing we haven't done that much. Leaving behind that hideousness, how about we go with the spring that has a known thing, here we had fs equals kx to the 1/2 power. They give you a bunch of data. In order to get a straight line here, you have to choose some combination of, you could do fs versus root x. You could do fs squared versus x. I suppose there's other weird combinations you could do that would get you where you're going, but basically you need to linearize it, which does mean you'll need to calculate a thing that they don't give you. In this case, you can graph this in lots of different ways. So the first point is, did you fill in things that would give you a straight line? And probably the two most common ones are force versus root x, or force squared versus regular x. So if you did that, give yourself a point. The second point here is for labeling and scaling your axes. They do have to have units on them. So if you're graphing your x-axis in root x, you do need to note that that is in square root meters or in meters to the 1/2. If you're doing force squared, your y-axis would have to be labeled in newtons squared. So make sure to put whatever the appropriate unit is there. It doesn't say this in the rubric. I will tell you on the AP exam, typically, if they give you a grid, they want you to use more than half the grid. Most people were fine on this, but like, be a little careful if they give you a bunch of data and you make a weird scale where your whole graph is like in like a tiny fraction of the grid. On the actual exam, they may not give you full points. They usually want you to use all the space, like make a good attempt to use a decent amount of space. So if you made a decent looking graph with axes and a sensible scale, award yourself another point. The third point here is for correctly plotting all 5 points. I was actually really surprised on the Quizam, the number, and I think it was a time issue, the number of people who only plotted 3 or 4 of the points. They gave, well, actually here they give you 6 points. So when I say all 5 points, there are in fact 6 points. So if you graphed 5 points, you were having a bad day. 3, 4. Okay, good. I graphed all 6, and then +1 for drawing a best fit line. Just like a free body diagram, when you see a graph on the exam, you should probably be pretty happy about it, because it's probably going to be 2 to 4 more or less free points for just being careful. It's worth noting, like, even if you graph the wrong thing, if you graph f versus x, you could still get 3 points here for making the rest of your graph well. Last but not least, you have to go ahead and find your slope and relate it to k. So again, your slope here, if you did fs over root x, that should just be k. That should just be your k value. In this case, I do typically like people who show their work for the finding the slope, like find a couple lattice points and like, you know, where it crosses the thing, and then like show how you're calculating the slope. It's worth an aside because you'll have Desmos on the actual exam. You can take the data, stick it in Desmos, and make a best fit line. That said, if you do that, and then they ask you to find the slope, and you're just like, boom, the slope is 47.6. You should probably tell it, you should probably write in your exam, where'd you get that number? What should you probably write? Yeah, Desmos gave me, right? Because otherwise they're going to think you pulled that number out of your butt, and that's not where numbers come from. So you got a point for finding the slope and attempting to relate it to k. And then you got a point for your k value should be somewhere between 47 and 53. There's a lot of different lines you could draw. If you were just outside that range, I guess you only get one of those 2 points. And it does have to be reported with proper units. So if I just wrote 47.6, I would not be right. It needs to be newtons per square root meter, because that's what we did. We did newtons divided by square root. So again, you might have missed the points for the log, but a lot of people I think are going to end up with like an 8 out of 10 for that FRQ, nevertheless, or a 7 out of 10 for that FRQ. All right, so take a moment, flip back to that first score page, and you can jot down your score there. And then let's go to the last one, which is both more complicated and less complicated, and is also only worth 8 points. So here we've got this motor dragging a chain along the ground. There is friction for once in this problem. and they throw a lot of numbers at you. And so the question here is, over that time interval as the chain is being retracted, is the rate at which energy dissipated by friction increasing, decreasing, or remaining constant with time? There's a lot of different ways to look at this. One equation that's going to be very useful to us throughout this whole problem is power equals force times velocity. Because power is, of course, is actually the rate at which energy is dissipated. So notice the velocity of the chain is constant. However, the force that the motor needs is not constant, right? Because if we think about friction, the force of friction as being kind of mu mg, what's happening to the mass of the chain that's in contact with the ground over time? It's decreasing. Because there's less chain, the force the force of friction is going down. The force of friction is decreasing over time. So this was a full 3 points for checking a box and thing. There is a point for checking decreases. There is a point for somehow relating. You could either just use the power equation or somehow correctly indicating the relationship between energy, distance, and time. And then the last point was specifically for noting that the force of friction decreases as the length decreases. So I think that a lot of people, yeah. In that, so 3 points available for that. The next one's a little interesting. The next one is a little interesting. And if you found the next one to be interesting, it is also 3 points. We're going to attempt to use that power equation. And specifically, we're going to look at this power equation, force times velocity. And I want us to think about the force from friction, right? I'm going to write mu mg here, but I'm going to come back to that m in just a second. Times velocity. Okay. So let's think a little bit about that mu mg. One way to think about that m is we could, and this is the way that I did it, you don't have to do it. You could think about sort of the linear density of the chain being mc over lc, in which case the mass that I actually have is going to be mc over lc times whatever x is at the moment. And x starts out at x0 and then gets shorter. But whatever my x is at the moment is going to be what I guess technically it's x0 minus x, but that actually doesn't matter. So I'm just going to leave my thing in there. So mu mg. The v is a little interesting. The v here is a little interesting. If we think about, okay, this is a little bit of a subtle point. If we think about the part of the chain that's in contact with the ground, the center of mass of that part of the chain is right in the middle, right? Okay, this is a little bit of an interesting point. If we think about the speed of the end of the chain as v, how fast is the center of mass of the chain moving? It's moving half as fast. So this is a weird point. The velocity here, I'm going to write this as 1/2 of 1/2 of dx dt. I'm going to write this as 1/2 of dx dt. Does that give me an extra factor of 1/2? What did I do here? I may have. No, that. Right. Is that good? I feel like I'm about to get an extra factor of 1/2 though from my x's. Oh yeah. Okay. That's actually not necessary. That's actually not necessary. We can just use dx dt here. This is fine. This is fine. We can actually ignore me. We're just gonna use dx dt here and everything's gonna be okay. We're just gonna use that as the speed of the chain. So that's my power. And notice we said that my power was changing. This is my change in energy over time. If I want to add up my dE dt to find my total energy, I actually have to do what? Yeah, I actually have to integrate this. This is where I'm going to take a moment and peek at my key and make sure that in my enthusiasm, I didn't mess something up because I'm feeling like I'm going. I feel like I have done a thing. So this is the part of the video where we'll cut to an advertisement. While I find my thing, scoring key. Yeah, okay, good. All right. Yeah, okay, great. So to find the total energy, we're going to integrate this whole thing. It's going to be mu mcg over LC. And the thing is, remember, power is energy as a function of time. So I'm going to put a dt at the end here. And the unusual thing here is what happens to my dt's? They go away. And so we can actually think of this as being an integral with respect to x from 0 to x0. So we end up with all of this stuff x0 squared all over 2 LC. There are some other ways to solve this question. You can also think of it as being positive or negative. They don't actually care whether it's positive or negative. This was a 3-pointer. There was a point for attempting to do an integral at all. So if some portion of you was like, I'm going to try to do an integral to solve this problem, congratulations. You earn a point for that. You get a point for noting correctly that the mass of the chain depends on x. The mass of the chain, at least as far as friction is concerned, depends on x, and then a point for the final expression. And if you didn't get any of those points, that is okay. Like this, these things do happen. These things do happen. All right. Last but certainly not least, are you looking for Mr. O'Neill?
No.
Okay, yeah. Last but certainly not least, we want to ask about the power output of the motor during this time interval. Hey, what did we say was happening to the rate of energy in the first problem? We said it was. What did we say? We said it was decreasing. Hey, guess what? The power output of the motor is it's being dragged at constant speed, which means whatever the force of the motor is equal to the force of friction. So whatever's happening to the work done by friction over time is also happening to the work done by the motor over time. So the power output is also decreasing. It's worth noting here, you get a point for a claim that matches part A. So if you got part A wrong, but you said the same thing here, you get that point back. A and C need to match. You need to be internally consistent. And then a point for specifically noting that the force decreases. In their derivation, they're like, oh, the net work done is 0. That is, any pulling force that occurs is the net work done on the chain is 0 because that constant speed. But basically, +1 for noting that the force decreases. So take a moment. You should now be able to total up everything from your test, all the FRQs, as well as all the MCQs. If you need help on scoring 1 and 2, I will record a separate video at another time. Thank you for your participation. I will And the